Welcome! In this session, we will explore an exciting problem titled Furthest Building You Can Reach. This problem challenges us to think critically about resource optimization and pathfinding strategies. We'll walk through the problem requirements, discuss possible approaches, and analyze their complexities. Let's dive in. In this problem, you're tasked with determining how far you can travel when given an array of building heights, a certain number of bricks, and a certain number of ladders. Starting at the first building, you aim to reach the last building, or the furthest building possible, by moving sequentially from one building to the next. To move forward, the next building's height must be greater than or equal to the current one. If the next building is taller, you can either use bricks, consuming the exact height difference, or use a ladder to bypass the height difference entirely. The challenge is to use these resources optimally to reach the furthest building possible, and the output is the index of that building. The output for this problem is a single integer representing the furthest building index you can reach. Let's take a look at specific examples to better understand the problem. For instance, consider an input with heights equals 4, 2, 7, 6, 9, 14, 12, bricks equals 5, and ladders equals 1. The output in this case is 4, meaning you can reach the fourth building under the given constraints. We'll break down how this result is derived in the explanation section. Here's the step-by-step explanation for the first example. Starting at building 0 with a height of 4, you move to building 1, which has a height of 2. Since this is downhill, no bricks or ladders are needed. Next, you move to building 2, which has a height of 7. This is an uphill climb, so you use 5 bricks to cover the difference. Moving to building 3, with a height of 6, is again downhill, so no resources are required. Now you attempt to reach building 4, with a height of 9. This climb requires 3 units, so you use your single ladder to bypass it. Finally, you try to reach building 5, with a height of 14, but you don't have enough bricks or ladders left to cover the difference. Therefore, the furthest building you can reach is building 4. Let's look at another example. With heights equals 4, 12, 2, 7, 3, 18, 20, 3, 19, bricks equals 10, and ladders equals 2, the output is 7. Here's why: starting at building 0, you use 8 bricks to move to building 1, as the height difference is 8. Moving to building 2 is downhill, so no resources are needed. To reach building 3, you use 1 ladder to bypass the height difference of 5. Moving to building 4 is downhill again, requiring no resources. To get to building 5, you use your second ladder to bypass the 15-unit climb. Finally, you use 2 bricks to climb from building 6 to building 7. However, you can't proceed further because you've run out of both bricks and ladders. The furthest index you can reach is therefore 7. Now consider the case where heights equals 14, 3, 19, 3, bricks equals 17, and ladders equals 0. The output is 3. Here's the step-by-step reasoning. Starting at building 0, you move downhill to building 1, which requires no resources. Next, you climb to building 2, consuming 16 bricks to cover the height difference of 16. Finally, you move downhill to building 3 without using any additional resources. Since you've reached the last building in the array, the furthest index in this case is 3. Let's discuss some edge cases. First, if all buildings are the same height, like in heights equals 5, 5, 5, 5, with bricks equals 0 and ladders equals 0, the output is 3 because no resources are needed to move between buildings. Next, if you don't have enough resources, such as in heights equals 1, 2, 100, with bricks equals 1 and ladders equals 0, you can only reach building 1 before running out of resources. Now, if you have exactly the resources required, like in heights equals 1, 2, 3, with bricks equals 2 and ladders equals 0, you can reach building 2, which is the last one. Lastly, for very large input sizes, the algorithm must still perform efficiently, even if the heights array contains up to 100,000 elements. To tackle this problem, one of the first approaches we can consider is the brute force method, which involves simulating every possible way to use bricks and ladders for each gap between buildings. The intuition here is straightforward. For every gap, we have 2 options: either use bricks to cover the height difference or use a ladder. By exploring all possible combinations of these choices, we can determine how far we can go. However, while this approach guarantees correctness, its computational expense is a major drawback. The time complexity grows exponentially, as there are two choices for each of the n1 gaps, resulting in O(2 to the power of n) time. Additionally, the space complexity is O(n) due to the recursion stack. This makes the brute force approach infeasible for large inputs, such as when n goes up to 100,000. Therefore, we need to look for a more efficient solution. An alternative is the greedy approach, which aims to save ladders for the largest gaps. The reasoning here is that ladders can cover any height, while bricks are limited, so we should use bricks for smaller gaps and reserve ladders for the largest ones. To implement this, we traverse the array and calculate the height difference for each gap. A max heap, or priority queue, helps us keep track of the largest gaps. Whenever we use a ladder, we push the corresponding gap into the heap. If we run out of ladders and encounter a new large gap, we replace the largest gap in the heap with bricks and use the ladder for the new gap. This approach is much more efficient than brute force, with a time complexity of O(n) log n due to heap operations and a space complexity of O(n) for the heap. While slightly more complex to implement, the greedy approach strikes a balance between efficiency and optimality, making it suitable for larger inputs. To further optimize the solution, we can use a min-heap to focus on managing the smallest gaps first. The idea is simple: by using bricks to cover the smallest gaps, we naturally save ladders for the largest ones. Here's how it works: as we traverse the heights array, we compute the difference between consecutive buildings and maintain a min-heap to store the gaps where bricks are used. If the heap size exceeds the number of ladders, we remove the smallest gap from the heap and subtract its value from the total bricks. If we run out of bricks at any point, we return the current building index. This approach offers significant efficiency improvements, with a time complexity of O(n) log k, where k is the number of ladders, and a space complexity of O(k). By focusing on the smallest gaps first, we maximize the total number of buildings we can reach, and the use of a min-heap ensures this is done efficiently. This makes the approach both optimal and scalable. When comparing the different methods, brute force guarantees correctness but is prohibitively slow due to its exponential time complexity. The greedy approach of prioritizing ladders for the largest gaps is more intuitive and efficient but doesn't handle all edge cases as effectively. In contrast, the min-heap strategy strikes the perfect balance between correctness, efficiency, and scalability. By limiting the heap size to the number of ladders, we ensure minimal space usage while still managing gaps optimally. This makes the min-heap approach the most practical choice for large-scale inputs, as it handles uneven distributions of gaps and maximizes the number of buildings we can reach. Overall, this strategy is the best fit for solving this problem efficiently and reliably. In this problem, we're tasked with determining how far we can travel across a series of buildings, represented by their heights. Starting at the first building, we aim to reach as far as possible by jumping from one building to the next. To help us make these jumps, we are provided with two limited resources: bricks and ladders. The challenge is to decide how to allocate these resources effectively for each jump to maximize our distance. We'll start by simulating all possible ways to use the bricks and ladders, a brute force approach that helps us understand the problem. First, we parse the input. The array heights gives the height of each building, while bricks and ladders represent our total resources. Initially, our position is set to the first building. From there, we simulate the jumps by iterating through the buildings one by one. For each jump, we calculate the height difference, diff, between the current building and the next. If diff is less than or equal to 0, the jump requires no resources, so we can move forward freely. This forms the basis of our simulation. Now, when we encounter a positive height difference, meaning a jump is required, we need to make a decision about how to allocate our resources. There are three options. First, we can use bricks to cover the height difference, which reduces the number of bricks by the value of diff. Second, we could use a ladder, which allows us to bypass the gap entirely, reducing the ladder count by 1. Finally, if we lack both bricks and ladders, we cannot make the jump and must stop our simulation at that point. Since this is a brute force approach, we explore every possible combination of these decisions. To do this, we rely on recursion or a stack to simulate all potential paths. At each decision point, we store the current state of our resources, how many bricks and ladders remain, and backtrack as necessary to explore alternate paths. Throughout this process, we maintain a variable called max_distance, which keeps track of the farthest building index we've reached across all simulations. Once all possible paths have been explored, the value of max_distance represents our final result. To better understand this approach, we can highlight a few key insights. First, only positive height differences matter. Negative or zero differences allow us to move forward without using resources. Second, ladders are generally more valuable for large gaps, while bricks are more suited for small gaps. This principle becomes particularly useful when exploring optimized solutions. However, the brute force approach does not consider this insight, as it exhaustively explores all possibilities. This exhaustive exploration results in exponential complexity, specifically 2 to the power of n, where n is the number of buildings. Such complexity makes the approach impractical for large inputs but valuable for grasping the solution space. To implement this, we use a recursive stack to simulate decisions at each building, along with state tracking to manage our remaining resources and current position. Key operations include calculating the height differences, updating the resources based on decisions, backtracking to restore previous states, and updating the maximum distance whenever progress is made. These steps form the foundation of our brute force simulation. Let's now consider some edge cases and the broader complexity analysis. First, if all buildings have the same height, no resources are needed, and you can traverse the entire array with ease. On the other hand, if resources are insufficient to make a critical jump, the simulation must terminate at that point. For a single building, no jumps are necessary, so the maximum distance is simply 0. Another key scenario involves large gaps, cases where the height difference exceeds the available resources, testing the algorithm's handling of extreme inputs. Analyzing the complexity, the brute force approach has a time complexity of 2 to the power of n, reflecting the exponential number of decision paths. The space complexity is n, primarily due to the recursive stack used for backtracking. While this approach is inefficient, it lays the groundwork for more advanced techniques. Optimized solutions, such as those using greedy algorithms or priority queues, can dynamically allocate resources based on the size of gaps, significantly reducing the computational overhead and making the solution scalable to larger inputs. This Python implementation solves the problem of determining the furthest building you can reach using the given number of bricks and ladders. The approach relies on a greedy strategy combined with a min-heap to optimize the use of ladders and bricks. 1. Initialization. Min_heap is initialized as an empty list. This heap will store the height differences, jumps, where ladders are used, allowing us to efficiently manage the largest jumps. 2. Iteration over buildings. The loop iterates through the heights array, examining each building and the next. The difference between the heights of consecutive buildings, diff, represents the effort needed to jump between them. If the difference is positive, uphill jump, it is pushed into the heap. This ensures we track all jumps that require resources. 3. Managing ladders and bricks. If the size of the heap exceeds the available ladders, the smallest height difference in the heap is removed, using heap.heappop. This represents the smallest jump where a ladder was used, and instead, bricks are allocated for this jump. Bricks are then decrement by the value of the smallest jump. If the bricks become negative, it means we cannot complete the current jump, so the loop exits, and the index of the last reachable building is returned. 4. Final return. If the loop completes without running out of resources, the function returns the index of the last building, len, heights, 1, indicating all buildings are reachable. ### key insights. The min-heap ensures that ladders are reserved for the largest jumps, minimizing the use of bricks. The algorithm efficiently handles the constraints by prioritizing resource allocation, ensuring it works for large inputs within the time limits. This implementation has a time complexity of n*log k, where n is the number of buildings and k is the number of ladders, due to heap operations. The space complexity is k, for the heap storage. This is the Java implementation of the furthest building you can reach problem, with the same logic as the provided Python solution. The code uses a priority queue, min-heap, to manage the height differences where ladders are used. If the number of ladders is exceeded, the smallest jump is replaced with bricks. The implementation includes type declarations and uses Java-specific collections, such as priority queue, to achieve equivalent functionality. Here, we start with the basic example where the input heights are 4, 2, 7, 6, 9, 14, 12, bricks are 5, and ladders are 1. First, we initialize a minute heap to keep track of the jumps where we use ladders, and we start with the given number of bricks and ladders. In the first iteration, at index 0, the difference between heights 1 and heights 0 is -2, meaning there's no upward jump, so we simply move to the next building. In the second iteration, the difference between heights 2 and heights 1 is 5. Since this is an upward jump, we push this difference of 5 into the heap. The heap size is now 1, which is within the available ladders, so no bricks are needed here. In the third iteration, at index 2, the difference is -1, indicating no upward jump again, so we move forward without using any resources. Continuing with the process, in iteration 4, the difference between heights 4 and heights 3 is 3. We push this into the heap, so the heap now contains 3, 5. Since the heap size exceeds the number of ladders, we pop the smallest jump, which is 3, from the heap. This jump is handled using bricks, reducing the brick count to 2. In iteration 5, the difference between heights 5 and heights 4 is 5. We push this into the heap, making it 5, 5. Again, the heap size exceeds the number of ladders, so we pop the smallest jump, which is 5. Using 5 bricks for this jump leaves us with -3 bricks, meaning we've run out of resources. At this point, we terminate and conclude that the furthest building we can reach is at index 4. Therefore, the output is 4. Now, let's examine an example where we have enough resources to finish. The input heights are 1, 5, 1, 2, 3, 4, 1000, with 10 bricks and 2 ladders. After initialization, the heap is empty, and we proceed through the steps. In the first iteration, the difference between heights 1 and heights 0 is 4. Since this is an upward jump, we push 4 into the heap. In the second iteration, the difference is -4, meaning no upward jump, so we continue. In the third iteration, the difference between heights 3 and heights 2 is 1, which is pushed to the heap, resulting in 1, 4. In the fourth iteration, the difference between heights 4 and heights 3 is 1. This is pushed into the heap, making it 1, 4, 1. As the heap size exceeds the number of ladders, the smallest jump, 1, is removed from the heap and handled with bricks, reducing the brick count to 9. In the fifth iteration, the difference is again 1, which is pushed to the heap, resulting in 1, 4, 1. The smallest jump, 1, is removed again and handled with bricks, leaving 8 bricks. In the sixth iteration, the difference between heights 6 and heights 5 is 996. This is pushed into the heap, resulting in 1, 4, 996. The smallest jump, 1, is popped and handled with bricks, leaving 7 bricks. Since we have enough resources, we reach the final building, and the output is 6. Finally, let's consider an edge case where there are no upward jumps. The input heights are 10, 9, 8, 7, with 3 bricks and 0 ladders. During initialization, the heap is empty, and as we iterate through the array, all the differences between consecutive heights are negative. Since there are no upward jumps, we don't use any bricks or ladders. This means we can proceed through all the buildings without exhausting resources. The furthest building reachable is the last one, at index 3. Therefore, the output is 3. To analyze the time complexity of the algorithm, we break it down into 2 main components. First, iterating through the buildings involves a single loop that processes the heights array. Since this loop runs n 1 times, where n is the number of buildings, it contributes an O(n) complexity. Second, we need to account for heap operations. For every upward jump, where the height difference is positive, we insert the difference into a min heap using heap.heapPush. Each insertion has a complexity of O log k, where k is the heap size, which corresponds to the number of ladders. Additionally, if the heap size exceeds the number of ladders, we remove the smallest element using heap.heapPop, which also takes O log k. Since there are at most n1 height differences, the combined heap operations contribute O(n) log k***. Thus, the overall time complexity of the algorithm is O(n) log k***. If the number of ladders, k, is small relative to n, the complexity approach is O(n), making the algorithm efficient for large inputs with few ladders. Now let's consider the space complexity. The primary factor here is the heap, which stores at most ladders plus 1 elements. This means the heap's size is directly proportional to the number of ladders, resulting in a space complexity of O ladders. Additionally, we use a few auxiliary variables like diff to store the height difference, or smallest underscore jump to track the smallest upward jump. These variables require constant space, contributing O(1). Combining these, the overall space complexity is O ladders, which is independent of the total number of buildings and ensures that the memory usage remains efficient. Let's compare this optimized approach to a brute force solution. A naive method would try every possible way to allocate ladders and bricks for each jump, evaluating all combinations to determine whether it's possible to reach the furthest building. This approach is highly inefficient because it explores all possible subsets of decisions, leading to a time complexity of O(2 to the power of n, where n is the number of buildings. The space complexity would also be high due to the need to store intermediate states. In contrast, the optimized approach avoids this combinatorial explosion by using a greedy strategy combined with a min heap. By prioritizing smaller jumps for bricks and reserving ladders for larger jumps, the algorithm achieves a much better time complexity of O(n log k) and a space complexity of O ladders, making it scalable and practical for real-world scenarios. Examining the best, average, and worst cases provides further insight into the algorithm's behavior. In the best case, where all buildings have non-increasing heights, no upward jumps occur, so the heap remains unused. Here, the algorithm simply iterates through the array, with a time complexity of O(n) and a space complexity of O(1). In the average case, most jumps are upward, but the number of ladders is small compared to the total number of buildings. This causes the heap operations to dominate, leading to a time complexity of O(n log k) and a space complexity of O ladders. Finally, in the worst case, all buildings have increasing heights, and the number of ladders is close to the total number of buildings. In this scenario, the heap grows to its maximum size, and every jump involves heap operations. Despite this, the algorithm maintains a time complexity of O(n log k) and a space complexity of O ladders, demonstrating its robustness across different input patterns. To solidify the time complexity analysis, we can mathematically derive the dominant factor. The most time-intensive operation is managing the heap, where each insertion or deletion takes O log ladders. Since the algorithm iterates through the heights array n1 times, we perform at most n1 heap operations. Multiplying these, the total time complexity becomes n1 iterations O log ladders which simplifies to O(n log ladders For space, the heap is the primary contributor, with a maximum size of ladders plus 1. This results in a space complexity of O ladders. Together, these analyses confirm that the algorithm is both time-efficient and space-efficient, particularly for scenarios with large n and relatively small ladders. When solving this problem, there are a few common mistakes that can trip you up. First, mismanaging resources, like using ladders for small gaps early on, is a frequent issue. This strategy can leave you unprepared for larger gaps later in the sequence. Instead, you should prioritize using ladders for the largest gaps and reserve bricks for smaller jumps. Another mistake involves skipping edge cases. For example, if the heights array has no jumps or consists of just one building, your code might encounter runtime errors or produce incorrect results. Always ensure you test these scenarios, such as a single building or buildings with identical heights. Lastly, incorrect usage of a priority queue, such as not removing the correct elements or failing to maintain the heap's properties, can lead to misallocated resources and wrong answers. To avoid this, ensure your heap always tracks the largest gaps and updates correctly after each decision. Now, let's discuss a few more pitfalls. Inefficient sorting or redundant iteration is a common way to increase time complexity unnecessarily. For instance, if your solution involves sorting or iterating through the data multiple times, it could push the complexity from O(n log k) to O(n squared, or worse, which leads to timeouts on larger inputs. Using a sliding window or a greedy approach with efficient data structures like heaps can help avoid this. Another common mistake is ignoring constraints and limits. If you overlook the problem's constraints, such as the number of buildings or the maximum height differences, your solution might work for small test cases but fail when tested against edge cases with large inputs. Always verify your solution against the upper bounds of the problem constraints to ensure it performs well under all conditions. This problem is an excellent example of making optimal decisions under resource constraints. It's designed to test your ability to use greedy strategies and carefully consider trade-offs between ladders and bricks. To excel, you'll need to master heaps or priority queues, which are essential for dynamic optimization. Practice inserting, removing, and updating elements efficiently, as this skill is crucial. During interviews, focus on clearly explaining your thought process. For instance, articulate why you're choosing to allocate a ladder to a particular jump instead of using bricks. This reasoning is often more important than just arriving at the correct answer. Also, be prepared to write and explain edge cases, such as scenarios with minimal input sizes, very large height differences, or situations where resources are exhausted early. Related problems like finding the kth largest element or merging sorted lists can also help reinforce the core techniques used here. There are alternative approaches to solving this problem that are worth discussing. A brute force simulation, for instance, tries every possible allocation of bricks and ladders. While this method is helpful for understanding the problem, it's extremely inefficient with a complexity of 2 to the power of n, making it impractical for larger inputs. A more refined method is the greedy approach with sorting, where you sort the gaps and allocate resources based on their size. However, the sorting step adds n log n complexity, and it may struggle to handle dynamic changes in resource allocation. The optimal approach combines greediness with a min-heap, allowing you to dynamically track the largest gaps and allocate ladders while using bricks for smaller gaps. This approach is efficient, scalable, and runs in n log k, but it requires careful heap management. Finally, a dynamic programming approach can also be used to track the maximum reach with a given number of bricks and ladders. While it guarantees correctness, it tends to be more memory-intensive and harder to implement. Great job! In this session, we covered the furthest building you can reach problem and learned how to approach it efficiently using a priority queue. Remember, optimizing for time and space complexity is crucial in technical interviews. Thank you for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!